So properties of solutions and expressing concentration. So let's do that. All right. So let's talk about the limits of solubility. There is a limit of solubility to most solutes. We have these conditions we call saturated solution. That means that the maximum amount of solute is dissolved in a solvent. Any additional solute will not dissolve. So I think of this often as here is, I used to do this when I was a youngster. We had big things of iced tea in the refrigerator, and I'd come home, here's this iced tea, and what I would do is I would start to put sugar in it. Now, remember that solubility is temperature dependent. So solubility is temp dependent. This iced tea was in the fridge, so it was cold, but I'll just keep putting sugar and stirring and stirring and stirring until there's a nice layer of sugar that is sitting on the bottom of my glass, and here's tea sitting up here. So at this point in time, I can't get any more sugar to dissolve in this iced tea, and so we would say that is a saturated solution. And it's saturated because I can't get any more sugar to dissolve. I've reached the maximum limit. Now, if I heated this up, this solution up, then I could get more to dissolve because as temperature increases and you stir those molecules up of the solvent, you can spread them out a little bit and get more solute dissolved into them. Such solubility is temperature dependent. Supersaturated solution, that's an unstable condition in which excess solute has temporarily dissolved. A minor change in conditions will cause a supersaturated solution to suddenly crystallize. So let's look at the same sort of situation. Now, this is not going to work so much with sugar, but I'm going to take a given amount of water and I'm going to put sodium acetate into it. And sodium acetate, this stuff right down here, I'm about to show you a video of it. And the other thing I'm going to do is I'm going to heat this solution up higher than room temperature. So room temperature is about 25 degrees Celsius. Let's say I heat it up to around, let's heat it up to about 40 degrees Celsius. There's actually a formula for exactly how to do this. I've done it a few times. I just can't remember exactly what temperature. Now I can actually dissolve more sodium acetate into the solution than I could at 25 degrees Celsius because, as I said, solubility is temperature dependent, and the higher the temperature, so if my temperature is a little bit higher, I can get more of that sodium acetate to dissolve in there. Now, I've dissolved what I think is all the sodium acetate I can get at 40 degrees, and then I cool it down, and I cool it down very slowly. And I'm really careful with this beaker. I don't jiggle it, but I just reduce it to room temperature at 25 degrees C. If you do this properly, none of that sodium acetate, that excess sodium acetate, will come out of solution, and your solution will be super saturated. All that means is there is more sodium acetate or more of whatever your solute is dissolved in the given volume of solvent in that solution than otherwise would be normally a saturated solution. And really all you have to do is do a minor change in conditions of this solution, jiggle it, add a little bit of energy in some way. You can even drop in what we call a seed crystal, and that seed crystal will cause that sodium acetate to crash out of solution, and what you'll get is a crystalline network. It comes out of solution. The whole solution will crash out and bonds will form. And actually, that solid that you now have, that crystallized solution, the temperature will increase because bonds are forming, and that's an exothermic process. So let's watch a video. Fun with sodium acetate. So what they're going to do, they've got a supersaturated solution of sodium acetate. All they have to do is put a couple of sticks in there, and that sodium acetate starts to crystallize on those sticks. Looks like matchsticks. And you can see that as the bonds form, the temperature goes up. Okay, so all you have to, there it is. All you have to do is disturb the solution, which adds enough energy to cause the solution to crystallize, and the temperature goes up, and it goes up because bond formation is exothermic. It releases energy. And so there you go. And they're building little sodium acetate pillars. And all they have to do is pour this supersaturated solution out, and the sodium acetate just instantly crashes out of solution because it's so unstable. And it gets hot. And there goes the rest. Just crystallized. Really kind of pretty. Hot ice. So those are two conditions of solutions: saturated solutions and supersaturated solutions. Before we go, I'm going to add one to it because it doesn't seem to be here in the PowerPoint notes. I bet it's on the next slide. And those are unsaturated solutions. And unsaturated solutions just means that if I have that beaker, and let's just make this some water, or we'll make it some tea like in the old days, and here comes some sugar, and if I dissolve and it all goes in at a given temperature, I haven't heated anything up, if all the sugar dissolves and there's nothing sitting on the bottom, then that solution is unsaturated. I have not reached the limits of the solubility of that solution. So because I can continue to dissolve more. All right, let's look at the temperature effects on solubility. As I said, solubility is temperature dependent, and for most solids and liquids, the solubility tends to go up, and here is just a graphical representation of the limits of solubility of a salt in 100 grams of water. So if we take 100 grams of water, and let's say we start out at 30 degrees Celsius, well, we can see this cerium sulfate, it's actually exothermic, and so its solubility goes down as temperature goes up, and it sort of reaches this plateau. But all the other salts, potassium chlorate, potassium dichromate, sodium chloride, potassium nitrate, lead 2 nitrate, and so on, all these other salts become more soluble. The solubility increases as the temperature increases. As we head in this direction temperature-wise, the solubility of that salt increases. So if I were to say, take some potassium dichromate here, and at 30 degrees, I'm able to dissolve, let's say that looks like about 17 or 18 grams of potassium dichromate in 100 grams of water, and then I were to cool that down very, very slowly to, let's say, 20 degrees Celsius, well, technically, only 10 grams of potassium dichromate should be soluble at 20 degrees, but let's say that none of it comes out of solution. Well, in that situation, since I have more potassium dichromate dissolved at 20 degrees than should otherwise be able to be dissolved at 20 degrees, that solution would be supersaturated. Okay? Because I have more potassium dichromate dissolved at 20 degrees, because it should only be 10, but because of our method, we dissolved about 18 grams at 30 degrees, and then we slowly cool down the temperature. Okay? All right. Now, while heating a solution tends to increase the solubility of almost all the liquids and solid solutes, it's exactly the opposite for a gas. So gases tend to be less soluble as the temperature increases. And you probably keep your beer or your soda pop, carbonated beverages, anything that's got, let's say, CO2 in it. And CO2 is a gas, and I'm just going to make this up. Let's say you can dissolve a certain amount of CO2, but as the temperature heats up, less and less CO2 can be dissolved. And this is in a unit called millimolar, which we'll look at a little bit, but not too much. But the concentration goes down. So CO2, or any gas, really becomes less soluble as the temperature goes up. Okay? So gases less soluble at higher temperatures. Solids and liquids tend to be more soluble at higher temperatures. That makes solubility of solids and liquids endothermic. All right, summarizing the heat effects. Heating a solution tends to favor free molecules. So if we go back and we look at gases, well, heating a solution up, gases are more confined. They're in a more ordered state when they're mixed in here, but if they can escape into the gas phase, then they can move to indefinite volume and indefinite shape. They can expand, and that increases their entropy. Their entropy goes up. Okay? Entropy increases as the gases escape. Liquids and solids will dissolve and mix, and that increases their entropy. So consider that liquids boil at higher temperatures. The gases escape, and the entropy increases as the liquids boil. So let's talk about some specifics. Here's Henry's law. It's the relationship between pressure and the solubility of a gas. We express it as Henry's law. So S subscript G is the solubility of the gas in the solution phase. That's the dissolved gas. Here is the partial pressure of the gas over the solution. K is the Henry's law constant, and it's unique to every solute-solvent combination. But this is the bottom line. As the pressure increases, the solubility of the gas increases, and it's really not difficult to understand. Let's say I've got a container and there's liquid in this container. We'll just make it half and half. So I've got some gas particles dissolved in the container. Try and mix them up a little bit. Okay, so there's 1, 2, 3, 4, 5, 6, 7, and then I've got some partial pressure here of gas that's sitting above the liquid surface in the headspace. and this is just where the gas is free. It has a certain vapor pressure up here, but we're going to make this special. I'm just going to extend this up here, and I'm going to make this a cylinder. So this is actually a piston that I'm going to be able to push down, and when I exert force in this direction, this is what's going to happen. So here is my liquid, and that's incompressible. Okay, so that's going to be the same, but I'm going to cut my volume in half. Now, I started out, well, actually, this looks like there's 6 in there. What I did was I cut the volume in half, and so what I did, if you remember the ideal gas law, I 2 times the pressure above, the partial pressure above the surface. So now all these guys, they squeeze in here really tightly. And what that does is it forces more gas molecules into solution. So now I'll have, so let's just double the amount. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and there's 1, 12. Okay, so we now have doubled the solubility. So we have 2 times the solubility because we have 2 times the pressure because we cut the volume in half here. Okay, so that in a nutshell is Henry's law. That's actually how they get carbon dioxide into a soft drink. This is really just sugar, H2O, sugar water, and the special seasonings and sauce and all that stuff. And so they put a hose on here. It's an automated process, and there's a hose going out to a pump which is pumping in CO2. And they pump up this head pressure so that CO2 dissolves in solution. So it's an easy calculation to determine how much partial pressure of CO2 they need to get a particular concentration of CO2 dissolved in there. So since solubility of the gas is equal to this thing called Henry's law constant times the partial pressure of the gas, and we know that this is an equivalency. So if this is a constant and we're only dealing with the solubility and the partial pressure, you could just say solubility 2 over solubility 1, and this would be pressure 2 over the partial pressure 1, and you could just cross multiply and solve for the unknown variable. If you are given a Henry's law constant, the units on the Henry's law constant will be molarity per atmosphere, and the units on pressure can be in atmospheres, so you could have molarity per torr. It could be molarity per millimeters of mercury. And so you could set your problem up. This is the solubility of the gas is equal to K, Henry's law constant, times the pressure. And let's just say that's in torr. And this is in molarity per torr. And then over here you have molarity. And so now there are your units, and let's just say you're solving for molarity. You just multiply the Henry's law constant, molarity over torr times torr, torr cancels, and you can solve for any of the variables of interest either way. You could be solving for the value of the Henry's law constant for that particular system. They'd have to give you pressure and the solubility of the gas at that particular pressure. Okay, that's Henry's law. It's pretty simple. Just remember that these are directly proportional, solubility of the gas and the partial pressure of the gas in the headspace.